Let's talk about the way I've been lying to you. Gotta come clean. Thing is, predicting radio wave propagation not nearly as easy. Oh, path loss exponent model. That'll give you a little point. Average path loss in the area will be plus or minus 12 dB, whole order of magnitude or more. But a lot of systems can live with that. And Professor Durgis gave us this other trick called the Seidel-Rappaport model, which allows us to get a little bit more accurate. 6 dB is standard deviation error. That's good enough for most error interfaces. Surely that is enough. All I need to do is plan for about the right energy level, about the right power, local area. Could be fine. We're going to talk about one of the ugly aspects of wireless communications. It's so ugly, it's a miracle it works at all. And I did share with you that one profile picture from a paper involving small-scale fading. That's what we're talking about today. This is the unfortunate aspect of physics. That makes the radio channel so very highly variable. You are in a realistic environment. And before I start, I'm gonna start with an optics experiment, a famous optics experiment from the 90s. It's called Elixir-Weidman experiment. Researchers in Israel that did a really interesting experiment involving the dual nature of light, the wave-particle dual nature of light. And the experiment goes a little bit like this. Let's say I have a laser. Oh, and let me switch to multimedia colors for your benefit. Shooting out a laser beam. And it goes through something called a 50-50 beam splitter. So that 50% of the laser goes this way, hits a mirror. Here. And get to another mirror. Actually takes 50% of this one and shoots it this way. And this one and shoots it this way. Comes down 50% of it. And then you have some photodetectors. Count photons. What do you see when you do an experiment like this? Well, my laser beam is a coherent source of light. It's not incoherent like light bulbs or fluorescent bulbs that are just sputtering packets of photons down at roughly the same frequencies but with random phases with respect to time. No, this is coherent light. Meaning a laser beam is going to make a light wave that really looks exactly like the plane wave expressions we've been using in antenna engineering class. Because antennas also are coherent radiators when they're connected to really well-disciplined oscillators, amplifiers, and excited with sine waves, pure sine waves, or stable sine waves with a little bit of modulation on it. Which means that the waves undergo constructive and destructive interference. So if I take 50% here and 50% here, the designers of this experiment arranged everything just so that this path experienced destructive energy. There was little to no optical power that made it to photodetector number 1. And almost all of the power, and because of constructive interference, made it to photodetector number 2. Okay, that's not surprising. Waves constructively and destructively interfere. But then they did something really interesting. They put a bunch of attenuators here. They kind of took one of the photodetectors, put it in there to measure, and started adding and adding attenuators. It's like one of those super sensitive avalanche detectors. You basically make photon detectors that can detect individual photons. Photon strikes an activated region. The old school devices, there would be a strong electrostatic field that would accelerate it and cause it to smash into another material that would release a bunch more electrons. And you would basically amplify a single photon and get a little blip out of it. Now I think they have some solid state versions of those same types of. Point is, like, you put in so many attenuators in there that now all of a sudden, instead of a coherent wave, you've just got a bunch of individual photons, just a sort of an occasional intermittent blip, 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 blip. That was a Poisson process. Right? So you just reduce the laser down to a trickle. The question is, when you remove the counter, what happens? Slow things down so much that these photons, which are traveling at the speed of light, zip through here, and there's what seems like an eternity. It's probably milliseconds between the times that one photon leaves the laser and hits this other one, hits one of these photodetectors before the next photon comes into play. So what do you think happens? Do you see constructive and destructive interference? Or, being quantum mechanically minded, the photon hits here, decides 50% of the time I'm going to go this way, and 50% of the time I'm going to go this way or this way. Same with this path. 50% this way or this way. That's not a reasonable outcome, an unreasonable outcome, to think that in the absence of any other photons to constructively interfere with, it would just quantum mechanically pick 50-50. 50-50 this way, 50-50 this way. And if you put your photodetectors there, you should just hear half the blip should wind up here and half the blips should wind up there. But of course, we live in a very weird world, and that's not what happens at all. It turns out that all the photons, no matter how much you slow it down, always go there. In other words, the environment is providing the information for resolving this quantum mechanical, not the presence of another photon doing that. The lesson to learn from the Elitzer-Weidman experiment is that no matter how insignificant a piece of electromagnetic energy is, it is still capable, even when it drops below photonic coherence, it is still capable of constructive and destructive interference. So, let's take this into the world of antennas. I have an antenna here. Let's pick somebody to be, I'm going to be the transmitter. Who in the audience wants to be my receiver? You volunteer for everything. The guy behind Jeremy, is it? Jacob? Jacob. Okay, Jacob. You're my receiver. How many pathways are there from me to you? I transmit antenna to your receiver. Let's see. We know one of them. We could calculate that one if we use the free space equation. We send a wave and it goes straight to Jacob. 1 over r squared loss is very easy. We look around this room and say, well, there are a lot of places that reflections ground, so there's going to be a ground bounce. I got some acoustic ceiling tile. I don't know what they do electromagnetically, but they're probably going to have a bounce a little bit of energy to you. I've got a wall over there. I've got a wall over there. If I've got an omnidirectional antenna, there's going to be something off the back wall that goes to you as well, right? Okay. Specular reflection. We could probably find a lot of specular reflection in this because it has 6 sides, 6 flat sides. What's more, there's these tables here that the waves can bounce off of to Jacob. And there's Jeremy. 4 regular scattering Jeremy. He's not going to create specular reflection, but he's going to scatter energy. It depends on how thick he is. So we send energy to Jeremy, it's going to scatter to Jacob. And then the guy behind Jacob, whose name I forget, Thomas. Oh yeah, Thomas. I'm going to send a wave to Thomas, and it's going to bounce to Jacob. In fact, I can send a wave, Jeremy, that scatters to Thomas, that scatters to Jacob, and contributes a little bit of energy to him, a little bit of power to the receiver connected to Jacob's antenna. And I can send some signal shoots over on the side. They can hit Thomas, scatter to Jacob. And I could go back and forth between Jeremy and Jacob 5 trillion times, and there still would be a non-zero amount of power that would scatter to Jacob. And according to the Elitzer-Weidman experiment, that power may participate in constructive and destructive interference. So if I ask you how many pathways, electromagnetically speaking, are there from my little transmitter to Jacob's receiver antenna, what would your answer be as an engineer? Infinite. Yeah, we can dream up these. We spend the rest of our lives, the rest of eternity, dreaming up combinations of pathways to get to Jacob. They all contribute. Now, at some point, they become so insignificant we don't need them to characterize the interaction. But the point of this little story is that there is always a little bit more, in some cases a lot more, what we would call diffuse RF power in the environment that you live in that contributes to small-scale interference. And so when I do actually go to operate at small scale or that wireless receiver in a realistic environment, you don't get one nice free space transmission equation wave. I get thousands of different amplitudes, waves, and polarizations striking my antenna, such that at any given moment, my received power is a random number. There's going to be an average power level, but sometimes it's going to be a good bit above that because a bunch of the waves are constructively interfered. Sometimes it's going to be a good bit below that. We call that a null, like when a transmission line. And if we drag this antenna, what's interesting about this is that if I hold the antenna still and the environment is still, then it turns out that I can hold that position for the end of time and I get the same amplitude
received at that antenna. So this is not a dynamic phenomenon unless stuff in the channel is moving and jumbling the phases of the constructive and destructive interference. So if I were to take the antenna and drag that through space, what I would see is something like this. It would look like a random process, unpredictable. It would have an average power level that would be predictable using the techniques that we've talked about in realistic environments. But you would have this small scale fading riding on top of this. And those peaks and nulls on average could be separated by as little as a quarter wavelength, just like a transmission line. It really is just like a transmission line, only unpredictable. Not just two waves contributing to a standing wave. It's an incredible three-dimensional standing wave in space. That's on polarization as well. So, my goal in introductory antennas class is to give you just some basic tools for how to handle that scenario. So, for example, this is hopelessly random, but we can still characterize the randomness of it and build our designs to that randomness. If you want to figure out how random something is, what kind of things do you characterize about it? What would you like to know as an engineer? What's the average? Good thing to know. The average power is the sum of the individual wave powers. You can show that pretty easily. What else would you want to know? Well, how about the PDF? You guys have taken the statistics class, right? The PDF. If I sit there at the antenna, I'm getting phasor voltage out. It, in this case, changes with respect to space or time. You're moving, that's time. If you're moving through, and you're just looking at the signals on an oscilloscope, it's time. But it's really space. You can translate. You can just do a little, for example, that's three-dimensional space. You can just say this is equal to the velocity time plus some sort of initial position x naught, and then substitute that in there, and all of a sudden you've got a time domain problem. So, how do we characterize this? What is this PDF? Well, let me introduce a couple of terms here. This is a voltage, the way I've drawn it. We've been dealing with field solutions in antennas class, which are really related to the voltages. The voltage you get at the terminal of an antenna is really proportional to the electric striking. Another thing that we're interested in, of course, is a phasor, because I put a squiggle on top of it. It's got an amplitude and a phase. Another thing we're interested in is envelope. That's probably the most important part of that. We care about the amplitude usually much more than the phase, because the amplitude is related to power. How do I get power from an envelope? Well, I would need to square it and divide it by some sort of impedance. Multiply 1/2, because that's how we do it with sine waves. And so 1/2 R, well, we could just say proportional to R squared. If I start bringing this, I need to know about hardware that the antenna is attached to, the receiver hardware, and I don't want to have to deal with that. I'm going to square to say that's power. What power is going to be proportional to the square? So armed with these definitions, let's figure out how this really affects power. Okay. This is an in-phase and quadrature diagram. The real part of a phasor and the imaginary part of it. The part you would just demodulate of the radio wave with a ideal cosine, and the part that you demodulate with an ideal sine wave. And you would normally plot voltage with an amplitude and phase. And the whole reason why multipath fading is so vexing is because to get to that end point that we measure here, you're actually doing a random walk where you're taking all the wave components that strike your antenna, all the crazy different directions that they point, and just kind of throwing them at random orientations and superimposing them till you get to a final result. So although you only measure one amplitude and phase there, there's really a line of sight to Jacob. That's a big one, and it happens to. And then there's a scatter from Jeremy, and that actually points in this direction. But then there's a bounce off that thing, and that actually. There's a bounce off the wall, and then to Thomas. Jacob points in this direction. And there's like a little tiny bounce off the laptop in the front that points in that direction. The point is you keep doing that. By the end of your random walk, you have to come down at some point. That's where you land. And if I move the receiver, then that jumbles the phases of all these components. Why you go from peak to null very quickly. Small scale failure. So if I wanted to model this, the best model to use for something like this is one that you antenna engineering students will have no problem grasping. My voltage at the antenna, two-dimensional space, is going to be the sum for I equals 1, lowercase n equals 1 to capital N. N, capital N, is the number of waves that I'm superimposing at my antenna, which we already said was probably infinity, right? You don't have to necessarily model all of them. There's going to be a lot of them. And they're going to be like little plane waves. They're going to have amplitudes that are constant, E sub n. You're going to have exp to the minus j k sub n hat dotted into r, direction of propagation. This is the wave number, 2 pi over lambda. And some random phase offset, however long it took them to get to that location. This is really the random part of the whole thing, or your position, right? Both changing the position or just changing the environment automatically changes the phase going from one transmitter to the next. So, let's break this down. Let's apply some Euler's identity. I can break this into a sine and a cosine. Cosine plus j sine. This is what I'm going to do. Yes. Cosine. R plus a random phase. And then another part of the summation term. And is it going to be a j in the front of it? So I got all my real value terms, a bunch of stuff added together, plus j, all of my imaginary value terms, a bunch of stuff added together. Now, if I take a bunch of random stuff and add them together, what do I get? What distribution does that resultant value tend to follow?
Gaussian. You didn't even have to think about that, right? Like the answer is always a Gaussian. To an instructor, to an academic, everything is just a bell curve. The grades, the height distribution in the class. It's always the safest answer in academia. By Joe, is the same thing. This is Gaussian. How did you know that? You just guessed. Yeah. You've been trained well. Good job. I would basically invoke the law of large numbers. If I have a bunch of random things that are independent of one another, and I add them together, I tend to get a Gaussian. What's more, this, I'll just call X, summation term of that, and this, which is basically another Gaussian. They're going to be two independent Gaussians. One in X and one in Y on my IQ diagram. So, imagine then I conduct an experiment, a dart throwing experiment. Let's say I have very good accuracy, not very good precision. Okay? Where I look at this and I'm going to aim for the bullseye here. That's what I'm aiming for. But I'm not very good. I have sort of a pitch in my throw and some shakes and some things. Luckily, I'm unbiased, but I'm going to have a Gaussian distribution in my X error. And it turns out I have an exact same Gaussian distribution error in my Y displacement as well. If I started doing this experiment where I started throwing a marker, basically marking every place that I hit, what distribution would that follow? Well, let's see. My X displacement, my Y displacement, or Gaussian. So the real question of what I'm asking is, what is the square root of the sum of two squares of Gaussians? And that is a very solvable limit. I'll put some notes on mine how to do that. But the probability density function of R, special name, looks a little bit like Gaussian distribution itself. Except it's got this row term out in front of it. Does anybody know what that distribution is called? In it in your comms class, or teach a wireless comms class, or touched upon. This is called a Rayleigh distribution. Show you what it looks like. This U here is a unit step function, by the way. But basically, it's always positive. You can't get negative envelope, right? So the Rayleigh distribution looks like this. Rho is my index to my random variable F. Rho, my PDF, like this. Where sigma squared is the standard deviation. Sigma is the standard deviation error for your X and your identically distributed Y errors. The mean of the Rayleigh distribution is sigma squared.
RMS. So this is with respect to envelope. If I do the transformation to power, where P is equal to R squared, then that turns into a different distribution. Well, P, now on my axis here, which is power, in watts, whatever linear unit you want to use, this distribution turns into exponential function. F of P, capital P, we always make the random variables capital, common convention, and the indexes of lowercase versions of the same variable. exp the minus P over P average. U of P, we need to divide by the constant PF to get that to be normalized to a true PDF. The average is somewhere in there. Now, this is a very valuable tool. Let me show you how to use this really quickly. When you can statistically describe something, you may not be able to fix every communications link, every antenna exchange that you come across, but you can at least appreciate for how often you could expect it to fail, right? Okay. So let's say I have an antenna and I know what the local area power is. Sum of all the waves on average, striking that antenna. Maybe I predicted it with one of the techniques that we talked about in class. Maybe I went and measured it. I averaged a bunch of measurements instantaneously that I made over a window of time in a local area. I'm going to use that term a lot, the term local area. It really just means an area that's about 10 to 20 wavelengths in scope. That in that region, we don't see typically a big change in the large scale average power. All the stuff that kind of looked like plane waves over here looks like plane waves on the opposite side of the local area too. Just nothing's changed that much, but you'll still get potentially a lot of up and down interference. Okay, so here's my antenna. Let's say I have this power here. How do you deal with small scale fading? Well, one way is to just build extra margin into your radio link between antennas. Say, I'm going to plan to receive P average, but I'm going to say that P average is 10 dB above dB above what the minimum amount of power that I need to do communications. So, in fact, as a name in radio communications, it's called your fade margin. The equation that I wrote is in dB. So let's say I had a 10 dB fade margin. I apply a 10 dB fade margin to my link. How often will I avoid a small scale fade?
If I'm just sending packets to a phone, walking through this environment with 10 dB phase margin, how many of those packets will I drop if I need P-min to do communications? Let's calculate that really quickly. The scenario is I have a P-min, and I have a local area where the average power is 10 dB higher. So that gives me a 10 dB, a factor of 10 in the linear scale as well, of a fade margin for my link. So I have a PDF. You know that P average is equal to P min plus F. Another way of saying that is that P min is 1/10 P average. Now, if I'm dealing with power, I'm going to use this exponential distribution. To estimate how often my link fails. And the way I do that is by marking my fade margin error. Fade margin threshold. Let's say this is my average, and I said we've got a error is going to be down here at 1/10 the average. And according to my probability density function, the area under the curve at this sliver is the probability that I will be below the minimum required power, right? So in order to calculate that, I just have to integrate from 0 average over 10, 1 over P average, exp to the minus P, P average, BP. So let's integrate this. Integration of an exponential is just an exponential, but I have to chain rule this puppy. And I have to evaluate it at the limits when there's going to be a negative sign. Negative 1 over P average out. Okay. When I integrate these limits, I'm going to have negative EX minus P average over 10 divided by P average, which is just exp to the minus 110 plus exp to the 0, 1. So basically 1 minus exp to the minus 1. Let's calculate that really quickly just to give ourselves a feel for what a fade margin looks like. Point 1, give xp, subtract that from that is 0.95. Oh, something didn't seem right about that. Always a problem when a professor does real-time math. So, slightly less than 10% of the time, under these constraints with a 10 dB fade margin, I'm going to lose a packet of data. Really pretty crummy, right? That's not great. And that's true. I think most fade margins, if you want to be conservative, anywhere from 14 to 19 dB or more, what I've heard engineers practically say. That'll probably get you down in just a couple of percentages. And then you can just rely on at some point you can rely on an acknowledgement and reply system to say, hey, I dropped the packet, transmit it again. And the way modern day communication systems work is that That's almost so fast you can't even tell even if you're doing real-time speech. But there comes a point where you just get so many errors. If 1 in 10 packets have to be acknowledged and retransmitted, then you're going to overwhelm your communication. Viable. But that's nice, just using some basic statistics and some reasoning. We're able to do a stochastic analysis on this problem and gauge with hard numbers what the probability of failure of the link is due to this phenomenon. Now what I've outlined here is Rayleigh fading. And we find it's actually a very, very good, even though we kind of derived it off the cuff with some very simple math assumptions, it is a remarkably good fit to the statistics of the envelope of an antenna terminal in a non-line of sight environment. So, if you're out there in the world and you can see you can't see your transmitter that you're communicating with, got a receiver in your hand, or vice versa. If you're the transmitter or the receiver, you can't see. Generally speaking, this is a fantastic model to describe the statistics of that scenario. If I have a dominant path, and we'll maybe spend a little bit of time after the test in a couple of weeks talking about this. If I have a dominant path, like a line of sight, then this doesn't hold so well. Because I usually have a lot of random stuff and one really big component going from my transmitter to receiver. And it turns out that winds up violating the law of large numbers. The law of large numbers says you've got a bunch of contributions that themselves are relatively insignificant compared to the mean. So as soon as you have a dominant line of sight component, you have something that's not trivial with respect to the mean. Maybe 10 dB higher than the diffuse power. That doesn't mean that's not what you're not going to see small scale fading. It just means that it'll follow a different statistical distribution. So now let's talk about some practical questions. How do people deal with this? Remember, I showed you a picture of small scale fading. It was last week. In that paper, there were some captures, like 5.8 gigahertz, moving an antenna out. And there was like 50 dB of swing there. How do we handle that situation realistically? Or how would you handle it if you were designing an iPhone or a Samsung Galaxy? What would it have to do? Well, first of all, we'd have to have a lot of automatic gain control in its RF channel because the dynamic range of signals can vary so quickly and so frequently. The amplifiers, you need to be able to tune them up and spin them up and spin them down, adjust the gain on the fly. That's one way to deal with it. Another way, of course, is fade margin. If you blast enough power, you can sure you only get 0.1% of the time that you're in a fade, or 0.01% of the time, although there's limits to how much you can play that game, obviously, and still be safe and still be within the confines of the FCC. So what other ways can you think of? Well, there's another technique called antenna diversity. This is a wonderful way to overcome this problem. And some of your phones do this, some of your laptops do this, most of your base stations do. What did we say the base station was? Unfortunately, antennas have gotten so cosmetic over the years. We're afraid to have things poking out of their boxes so you can't see what they're actually doing. But I guarantee that base station hovering above us has quite a few antennas in it. And one of the reasons it does is so that it can employ something called antenna diversity. Just do a quick thought experiment. Let's say I've got this terrible multipath. I'm in a non-line of sight environment. I've got a receive antenna. There's a 10% chance I'm going to be in a fade. I get way more than you do.
But if I have another nearby antenna, and we said you don't have to separate these very much before you get a completely independent sample. This is a null, this is a peak, this is a peak, null, this is a peak. In fact, once you get past maybe a quarter wavelength, you have almost independent samples in a true multipath rich Rayleigh dating environment. Now I have two antennas side by side, and I get to pick the best one or combine them in a way that I would like in an optimized way. What is the probability that one is in a fade? It's 10%. Probability the other one is in a fade. It's the exact same environment, so it also has to be 10%. If they're independent, though, what is the chance that both of them experience a fade? 1%. That's right. Multiplicative probability of independent events. And the third one, it would be 0.1%. Fourth one, it would be 0.01%. So by adding antennas, you can almost arbitrarily push down the reliability, so it's very good. Now, that's not the only thing going on. Base stations that have multiple antennas. Maybe one day, when I'm not filming myself in this court evidence, we'll climb up there and take the covering off that, and we'll see exactly what this Cisco is made of. Nobody will tell OIT campus environment. But if you were to crack that open, you would probably find 3 or 4 or 5 or 6 antennas. Partly because they're using diversity, and they're also using this thing called MIMO, where you shoot beams in different directions, bounce signals of information off of different environmental structures. Use multipath to your advantage, the fact that you have multiple data streams going to different users. And it turns out that if you do it in the right way, each of those streams has n element diversity gained from those antennas in there.